In this work, we introduce a novel approach for automatically optimizing product placement for virtual stores. Based on a regressor trained with eye tracking data, our approach optimizes the product placement for virtual stores. Here is an overview of our approach. The input is a virtual store scene and some 3D products, and the output is a virtual store with our optimized product placement. The product placement optimization includes a cost function, consists of an exposure cost and a spatial cost. Given an input scene and some virtual products, we perform a pre-processing step to obtain an initialized store scene with randomized product placement. The optimization is driven by a cost function, which considers an exposure term, encoding our regressor to improve product exposure, as well as a spatial term concerning design priors. First of all, to train our exposure prediction model, we created an product exposure dataset. As users navigate our environment, the exposure of each product is recorded. We use products' features, including their size, their texture intensity, their height from the ground, and their locations to train a regressor. After the training process, we can estimate exposure of a virtual product placed at a certain location in 3D virtual stores by running the regressor. Spatial term. Including interval, visual balance and crowdedness. Interval constraint places products with equally spaced intervals on the shelves. Visual balance constraint keeps visual balance by placing large products at lower locations and small products at higher locations. Crowdedness constraint avoids too many products on one shelf. Product placement optimization. Then the optimization process in this project uses a Markov chain Monte Carlo algorithm. Finally, we obtain a virtual store with our optimized product placement. Our optimization framework provides practical interfaces for retailers, and allows them to control the placement synthesis process partially. For example, the retailer may want to promote certain products. Our optimizer will prioritize placing these products at locations that are more noticeable to enhance the product's exposure by adapting the exposure weights. In some other cases, the retailer may want solutions to include products placed at specific locations. Using hard constraints, the retailer can fix the locations of certain specific products. And our optimizer is asked to modify the locations and orientations of the other products. Here is a synthesized clothing store. Here is a synthesized toy store. And here is a synthesized grocery store. Using a qualitative scene rationality evaluation, we evaluated placement realism, placement convenience and satisfaction of users in store experience. Our synthesized result shows a low difference from the result created by designers. The result also shows our approach is more effective than the other two compared approaches. We also conducted a quantitative product exposure evaluation. It evaluated the exposure improvement effectiveness of our approach. The product placement synthesized by our approach shows significant improvements in total exposure time than our approach without spatial cost and our approach without exposure cost. And there was no significant difference between our approach and the designer approach. In addition, we record the corresponding product exposure data viewed by the participants. Then we analyzed participants' different behaviors in the store scenes synthesized by the different approaches. We further evaluated how each spatial cost term affected the results using an ablation study. The results suggested that the lack of any spatial constraints would cause significant performance degradation over all of the metrics. Here are some results. This is the end of our video. Thanks for watching.